Welcome. I'm here to introduce to you Prateek Joshi, founder of Pluto AI, a water management platform powered by deep learning. Prateek Joshi is the author of 4 books. He's a TEDx speaker, and tonight he's going to talk with you about the use of deep learning to analyze time series data collected by Internet of Things sensors. Welcome, Prateek.
Hi, I'm Prateek, and I'm going to be talking about deep learning for Internet of Things. Now, before we jump into how deep learning is relevant for Internet of Things, let's talk a little bit about data. Now, when we look at the spectrum of data types, there's basically images, there is text, and there's sequential data. Now, I know text is by nature sequential, but I'll just lay it out this way because it kind of illustrates how data is spread across the spectrum, and most of the times in the real world we encounter data which is in one of these formats. Now, all the research, or rather most of the research in deep learning is heavily focused on images and object recognition, and that's where convolutional neural networks have been highly successful, and we see applications in say self-driving cars, and there is biometric systems, a lot of things happening here. And similarly in text, a lot of people use this deep learning in like search engines, text analysis, topic modeling, many different things. And then there is sequential data. Sequential data where, for example, sensors and finance, speech, and so on. Now, when you look at the overlap, that's where it becomes very interesting. When you look at the overlap of these various different types, when you look at image and sequential, like video comes out. So because when you look at video, if you analyze each frame independently, you're missing out on a whole bunch of things, and that's where the sequential part comes into picture, because what happened in the previous frame is very relevant to what's happening now, and that's where if you take advantage of the temporal structure of data, it's going to be very useful in modeling this. And similarly, when you talk of natural language processing, it's if you understand the context of a sentence or a page or a document, it becomes really important. The sequential component is very important. So, and in the middle of all this, for example, an application is human-computer interaction where a cognitive system needs to recognize the face, understand what the person is saying, the speech, and there is text, and many more things. So all the things come together to build a cognitive robot, right? Now, let's zoom in into the sequential data. Now, let's talk about a particular manifestation of sequential data. So we'll talk about time series data. Time series data is nothing but time-stamped readings generated from a data source, like sensors, microphones, log files, and many more, right? And this time series data, as we encounter this, and again, we talked about this, sensors, finance, and speech. Now let's zoom in even further. Now, sensors, it's basically a device that can measure a physical property and respond to it, right? For example, it can measure water flow, temperature, pressure, vibration, soil moisture, you name it. There are many different parameters that a sensor can measure, and sensors have been around for a very long time. Now, if you go back, like say 25 years ago, when these devices become more and more relevant, they were bulky, right? They were expensive, and deploying it was a very capital intensive process because it's just the hardware was not there yet. And that's when people started thinking, like, okay, hey, what if I have like thousands of miles of pipes and you install a sensor somewhere, like how do you get those readings? The only way is that you send a guy, and the guy goes there and he looks at the readings and he comes back. Imagine doing this for like 1 million sensors. It's not going to happen. And so people started thinking, how do we get this information and be more efficient, because we don't want to waste all that time? And that's where the Internet of Things comes into picture. Now, Internet of Things, it's just an ecosystem of internet connected devices, right? So imagine if that sensor that's installed like 1,000 miles away, it can wirelessly communicate to the cloud and can do it continuously and automatically. So you don't need a person to go there and get those readings. And this is why this whole paradigm is picking up really quickly, because it allows you to monitor a vast network of infrastructure just remotely, and you can sit in your office and get all those readings. And And let's talk about the thing. Now, the Internet of Things, this is the thing. The Internet connected wireless sensors that can continuously emit timestamp data. So for example, as we talked about it, temperature, water flow, pressure, vibration, soil moisture, many more things. And this thing it manifests itself in various different forms. Sometimes they plug in multiple sensors on the same device. Sometimes it's an individual sensor, it's installed, there's an array of sensors, many different things. Right. Now that we know why we need Internet of Things, let's dig a little deeper into the tech stack of the Internet of Things, because all of this is kind of leading up to why we need like a deep learning kind of framework to analyze this data. Now, when you look at the tech stack of Internet of Things, there's many things going on, right? This is a higher level abstraction where between the thing and the end user, that's basically the graph or a chart. We have many different things. There's communication protocols, and then there's cloud-based software, and then there's the end user, right? Now let's dissect the stack. Now, when the thing communicates with the gateway. Now, this is a very important layer. Now, let's take an example, right? Now, let's imagine there's a farm, like an agricultural farm, and they've installed a whole bunch of soil moisture sensors. Now, for each of those sensors, if you want them to communicate to the cloud, you need to install a certain processor, which means that it costs money. So you cannot install like 1 million sensors and put that processor on that device, because it just breaks your profit margin. You cannot hope to deploy that at mass, and that's why we have a central command. Its gateway is basically a device that controls say a bunch of sensors. So let's say in a farm, if there are 1,000 sensors, those sensors communicate with the gateway, and the gateway communicates to the cloud, and that's why it becomes way more efficient, and only the gateway needs to have the processor to communicate to the cloud. Right. Now, after that, the next layer is connectivity. Connectivity is basically, is it wireless, is it wired? And then after connectivity, there's link protocol. It's basically, is it CDMA, is it Wi-Fi, is it Bluetooth? And then after that, there's the internet protocol. Is it IPv4, IPv6? Given the number of devices that are, it's just exploding, we're definitely heading towards IPv6. And then there's the communication protocol. It's basically like a queuing protocol where is it AMQP or MQTT, very standardized. Right, so now the data has trickled through all these layers, and now we are entering, it becomes a number here, right? Now this layer is data ingestion. Now, if there are only like say 2 sensors emitting data, it's fine, we can handle it. But when there are million sensors all emitting data simultaneously, we need some kind of data ingestion tool, and that's where tools like Spark Streaming or Apache Flume or Kafka become really relevant. Now, after ingestion, we need to store the data. Data storage usually happens in a time series database in this situation, for example, InfluxDB or OpenTSDB. And then the data access part is when you want to access the data in real time and maybe visualize it, extract rolling statistics. And then intelligence part. Intelligence is where we build our sequence learning models and do meaningful things with it. And then the application part, like for example, do you want to detect anomalies? Do you want to detect leakage? Do you want to forecast something? And then it becomes a nice chart or a graph or an SMS alert, right? And that's how the data goes from like a physical measurement to something very meaningful for a business. Right. Now, the next question is, why do we need time series analysis, right? Because when people say that you install a sensor, and if let's say you install a temperature sensor, and if the temperature goes above a certain value, you do something. If it doesn't, don't do anything. Like a simple conditional monitoring thing, right? People say that, hey, why don't we just do that? Why do we even need to analyze, do fancy things with it? The problem is the complexities of modern data. It's just thresholding, right? That approach is not enough. You got to do way more, and that's why we need some kind of time series analysis tools to extract more meaningful information. Like for example, extracting relevant features, understanding the past, predicting the future, and exploring the relationship between multiple data streams. Now let's dig a little deeper into the properties of time series data. Now, the reason convolutional neural networks became so widely used, so successful, is because it takes advantage of the fact that image is a 2D structure, right? If you take that out, before CNNs came along, people were kind of taking a 2D image, creating a 1D array and pushing it out. But convolutional CNNs take advantage of the fact that it's a 2D structure. So similarly, we need to understand what properties, or rather what is it within time series data that we can take advantage of, and then do smart things with it. So a couple of examples are, for example, there's trend, in the sense that is there a trend to the data? Like, for example, there's a sine wave, but if the sine wave is increasing, this becomes a trend. And is there seasonality to it, in the sense that, hey, something happens in the summer, but it doesn't happen in winter or fall? And are there irregular movements? And are there long-range cycles that are not related to seasonality? How does the variance change over time? Are there outliers? If so, how bad are they? And do we need to remove it? So many different properties of time series data contribute to how we build our models. Right. Now, before we kind of we jump into how we use those properties, let's understand a little bit about the stationarity, because this heavily impacts how we build our models, right? Because when we look at time series data, one of the most I would say popular, right, one of the most interesting applications is predicting the future. What people want to do is, hey, I know everything that happened until now, and I want to predict the future. So to that end, a stationary process is basically the parameters such as mean or variance and autocorrelation function, they don't change over time. That's an example of a stationary process. Why do we care about stationarity? Because stationary data lends itself very nicely to things like prediction and forecasting. Right? If the data is not stationary, your models are going to give spurious results. It's just, you cannot build anything meaningful if your data doesn't behave properly. Right? And that's where we come to non-stationary processes. Non-stationary process is, again, a data that if it's not stationary, the parameters such as mean and variance, they don't remain constant over time. That's a non-stationary process. Now, there are many different types of non-stationary processes here. For example, there is Brownian. It's just random walk, right? And then Brownian with drift. Basically, it's a random walk, but there's a constant drift associated with it. And then there's trend stationary. Now, this is actually a very interesting concept. If the data, let's go back to the example of a sine wave. Very simple example. Let's say there's a timestamp reading of a sine wave, but it's slowly increasing like this. So as a human, if you look at that waveform, you know exactly what's going to happen next. But for a computer, you need to kind of explain that, hey, this is trend stationary, in the sense that you need to remove the trend, make it stationary, and then computer will be able to understand how to predict the future, right? It's called retrending. And again, cyclostationary are the parameters, are the cycles to the different stationary, in the sense that the original time series variable is not stationary, but if you take the delta between consecutive timestamps, it becomes stationary. And again, trend stationary, Brownian with drift, it's a combination of these things. Now, these are various different types of non-stationary processes. And the interesting thing is, some of these can be converted to stationary by applying some techniques. And that's very important when you build your models. Right. Now, let's understand how do we find out the stationarity, right? So that's where the concept of shock becomes important, because a shock is basically, if you look at a time series data, and at t is equal to t naught, an unexpected event happens, and that's what's called a shock. So for example, let's say there's an input variable x, and that's translated to an output variable y through a function f. It's a very simple, nice relationship, and that's called a null model. Now, at t is equal to t naught, you punch it in the face, right? Which means you have a shock, and then if it's a stationary process, it's going to come back to its original form. That is, as in, it's going to revert to its original mean and variance, and it's going to just continue going. But if it's a non-stationary process, a shock is permanently going to change the course, right? And that's why the reaction of a time series variable to a shock is very indicative of stationarity, right? So now, stationarity is not like you can't look at a CSV file and just infer anything about stationarity, because it's not like 10 values. You have a huge file with like a million values. And to a human, it'll all look like noise because the waveform just changes. So to formalize this process, there's something called a unit root test. A unit root test basically tests whether or not given time series variable is stationary or not. And it's a very deep topic. I'm not going to dive deeper into it, but basically the gist is there's a test that you need to run to test whether or not a given time series variable is stationary. Now, okay, so all these things that we discuss is part of like pre-processing, or rather doing your due diligence to understand what we need to do with data before we model it. So now we come to the modeling part. There are a whole bunch of like popular techniques, there are a whole bunch of others too, but the progression is basically this, like moving average, autoregressive models, autoregressive moving average, autoregressive integrated moving average, hidden Markov models, recurrent neural networks. We're going to quickly walk through it and understand how, or rather, what are the shortcomings of each model, and then how we arrive at recurrent neural networks. Right. Now, the most simple example is basically moving average. It doesn't work in most cases, but it's been around for a long time. It has served us well. So it's basically like a moving window. You set a window size, you take the average, and you keep going forward. It's just, it doesn't tell you much, but it's just very easy to calculate, and it's just been around for a long time. Now, next is autoregressive models. Autoregressive model is a model where the output depends linearly on its own previous values, as in you regress over its past n values, and of course there's a probabilistic variable associated to it. And then there is autoregressive moving average, where you describe a time series data in terms of two polynomials. One is autoregressive, another is moving average. But one of the problems of ARMA is that it doesn't take care of non-stationarity, and that's why they introduced autoregressive integrated moving average, where you say that, hey, I'm going to introduce a differencing component to remove non-stationarity. But one of the problems here is it assumes that differencing is the only way to remove non-stationarity, which is not true, because non-stationarity can happen for many different reasons. So that's why we people started working on hidden Markov models, right? Hidden Markov models have been around for a while. They have served us well for a long time. People use them for many different applications, like speech recognition, finance, epidemiology. What this does is basically we assume that the underlying process is a Markov process, right? Markov process is basically like with hidden states, in the sense that you assume that there are n states, and the underlying system keeps going between those n states, and you see the outputs. Our goal is we observe the outputs, and then we try to infer something about the state transition of the system. But hidden Markov models, they have some very, very important shortcomings. A couple of them are, number one, it assumes that the current state depends only on the previous state or previous n states. Right? It's not true in real life. The transition probabilities are constant, in the sense that it doesn't, like the probability of going from state n to state m, it remains constant throughout the whole system. And it's not true, because a system evolves over time for many different reasons. So it's restrictive. And the next thing is the current output is independent of previous outputs, which is again not true in real life, because we want to impose that restriction on any real world system. And that's where we jump into deep learning for time series, right? All these shortcomings that we have discussed, we'll try to address it, how deep learning solves those issues. So obviously, we are going to use deep neural networks to model time series data. Now, as we all know, deep neural nets are really great at identifying patterns in data, and the architecture depends on the type of data we are dealing with. Right. Now, when you look at various different architectures, feedforward is basically the original technique, simple technique. It's just you arrange a whole bunch of layers and you push the data through. And then we got to convolutional neural networks that are great for images, like AlexNet, GoogleNet. It's a pretty famous model. And then we moved to recursive, where they're great at modeling like text data, and they're used extensively in natural language processing. And then recurrent neural networks that are really great at modeling time series data. Right. Now, before we jump into the recurrent neural network, let's discuss a couple of use cases. Number one, they're very useful for anomaly detection, demand forecasting, like for example, water or power demand, asset failure prediction, and leakage detection. Now, just to give a small example of how it works is, let's say if you want to detect water leakage, and let's say there's a huge tank, and there's like an apartment complex. The way it works is the water is supplied, and there's a regulator that converts water is coming in at say 80 psi, it regulates it down to 60 psi, and then you supply it to the building. And within the building, you open your sinks, your taps, and the pressure drops a little bit, right? And whenever there's a leak, right, the pressure drops as well. So the thing is, whenever somebody opens a tap or whenever there's an opening, it leaves a distinct pressure signature and it goes down. And your goal is to understand, is this drop in pressure, is this related to somebody or a whole bunch of people opening pipes, or is it because it is leaking somewhere, right? So that's a simple example of why we need a learning model to solve these problems. Now, one of the first questions we need to answer is, can we use feed-forward neural networks, right? The problem is, number one, they need fixed length inputs and outputs, so they impose that restriction. And number two is they ignore the temporal structure or time series data, right? And that's a very big restriction because you don't know how, or rather you don't want to fix the window size. You want your learning model to learn it, and that's why we go to recurrent neural networks. Here, it's an example of this is feed-forward, this is recurrent neural network. As we can see, each neuron takes its own output and trains itself. Now this is one of the most important differences, and this structure allows the recurrent neural network to model time series data really well, because time series data can have like arbitrary lengths of time, and that's why we need a structure like this that can learn from itself, right? And the training algorithm that we use to train recurrent neural network is called back propagation through time. And the reason is when you want to train a recurrent neural network, since it takes its own output, when you try to back propagate it, it creates like an infinite loop kind of thing, and that's why people use this technique called loop unrolling, where a recurrent neural network becomes a really long feed-forward network, and then you can use regular back propagation. But again, the problem is, since you unrolling a recurrent neural network in a time series framework, it expands into a really long feed-forward network, and that's why they use a technique called back propagation through time that allows them to train it within reasonable time. Right. So let's take a very simple example of how a simple toy RNN example works. So this is a simple time series like generated, and a simple RNN can simulate this data for arbitrary sequences. So this is a longer sequence, a short sequence. So it can kind of follow this structure once it trains itself, right? Now, the next question that we need to answer is, okay, so now that we know that we can model this data, how far into the history can we go, right? For example, do we need to go back like 10 minutes, 10 days, 10 years? You don't know, and we don't want to know. We want the learning algorithm to decide it, right? And that's the thing. So it depends on the problem at hand, and it depends on the memory of the time series data. Now, what is memory, right? Memory of a time series data is basically the rate of decay between 2 points on the time axis. As you increase the distance between them, the rate of decay of statistical dependence is called the memory of the data, right? And this is a very important concept because it's very important to understand if a given variable has long memory, right? So what they've decided is the rate of decay, the rate at which it decays, right? If it's slower than exponential, if it decays slower than the exponential, then it has long memory, right? If it's faster than exponential, which means it's decaying really quickly, which is good, and it's short memory. So to take an example, something that's slower than exponential is like a power function, y equal to n squared. Exponential is y is equal to 2 power n, and something faster than exponential is factorial. Now, as you can see, it's a discrete use case. So which means for the purists out there, the continuous use case here is again, power like is y is equal to x square, y is equal to 2 raised to x exponential, and this would be a gamma function. I'm not going to go into the gamma function details, but basically, if you look at the graph, it decays faster than an exponential function. Now, the reason the concept of long memory is important is because when you look at like time series data, like cause and effect, sometimes something happens at t is equal to t naught, and you see the effect, right, at t is equal to t naught plus x. Now, if this is short enough, then a vanilla RNN can quickly train it, and you can see the result. The problem is, what if something happens now and you see the effect like 3 days later, right, or 3 months later? You don't know. So how do we decide? How long should the memory be retained, right? And that's the reason we jump into LSTM cells. That's long short-term memory. One of the main advantages is that number one, it can remember a value for an arbitrary length of time, and number two, it can extract patterns in time series data with very long time lags, right? It's a very important thing to have when you're modeling time series data, because like for example, if you knew that whatever happens, for example, if you're looking at a sensor reading and you know that, hey, something happens now, I know a minute later I'm going to see the effect. That's good because you can set that. But in real world, it's usually like a whole array of sensors, and you don't know if it's 10 seconds or 10 hours. And that's why you need something like this to model that. Right. Now the next thing is, what about, can we help our RNN in some way? Can we pre-process the data so that the accuracy can be better? For example, some people use frequency domain transforms, have been around for a long time. So for example, you take, in speech, it's used a lot, right? You convert it into a frequency domain, like something like a Fourier transform, and then you use the frequency signature to do a lot of things. And there's again this windowing, in the sense that instead of taking every single point, you take the window and you do something with it, and you remove the outliers to make the data more consistent. The thing is, all these techniques, it's just, at least in our experiments, we found that frequency domain, that we as humans, we think that frequency domain works better than just raw data. And in our case, it didn't, in the sense that we don't want to impose our intuition on a deep neural net, because we want it, if the frequency domain is the answer, it will extract it, but we don't want to impose that restriction. So similarly, pre-processing with or without depends on the use case, but in our case, pre-processing didn't help the accuracy. Right. Now the next question that we need to answer is, where do we do these computations, right? Edge is basically the sensor, in the sense that any device that's actually measuring it, and versus the cloud, right? So it depends on multiple things. Number one, the compute power available at the edge, the bandwidth restrictions, and also the performance requirements. So sometimes, let's say, if you have to make really quick decisions, right? Not very computationally intensive, but you need it in real time. There's no time to send like a high-res image to the cloud, wait for the decision, and in that situation, maybe you got to put a heavy processor at the edge and make those quick decisions. But sometimes, if you have like really low-cost sensors and you cannot afford to have those high-end processors at the edge, then you got to stream the data to the cloud. The good thing is that they're just numbers, so they're not very intense on memory, and that's why the bandwidth restrictions are low, so you can send the numbers up and wait for the inference. So it depends on the problem at hand. And people have used both to their advantage. The answer is somewhere in the middle, as in the training happens in the cloud, the inference happens at the edge, so that you can minimize the amount of data that has to go back and forth between the cloud. So yeah, that's pretty much it.